And welcome to today's lesson. In this first tutorial, we are going to be able to graph more complicated rational functions. So we are still in sections 8.2 and 8.3, the second day of our investigation of rational functions. And again, we have our rational function that is any form p of x over q of x, and again, since we have a denominator, q of x cannot be equal to 0. So we have a little laundry list of all the stuff that we're going to be doing for our rational functions, and here is how to find them. Step number 1, not that you have to go in this order, but I like to go in this order. First, let's find and graph our vertical asymptotes. We find this by setting the denominator equal to 0. I'll say set denominator equal to 0. That's how we find any vertical asymptotes. Number 2, we're going to find and dash the horizontal asymptotes, or asymptote. This depends on the degree. In a previous tutorial, we talked about the degree of the numerator and the degree of the denominator, and there are a couple different cases for how to find our horizontal asymptote. Step 3, find and plot any x-intercepts. Now, x-intercepts are otherwise known as zeros, and zeros come from the numerator. We're going to set the numerator equal to 0, and that should give us any x-intercepts. Number 4, find and plot the y-intercept. The y-intercept will always be an ordered pair where x equals 0. So we're going to set x equal to 0, and we're going to have our ordered pair 0, comma, whatever the y value is when x is 0. And we can plot that. That's very helpful when we're graphing. Finally, we're going to plot, we've already plotted all this stuff and dashed in our stuff, and I call that the shell. Then we're going to plug into our calculator and fit the graph into our shell, our little skeleton that we've already created. Once we have our graph, we're going to state the domain and the range. The range can be a little bit tricky today. And then finally, we can do our end behavior. So if you get lost in whatever we're needing to find, come back to this list. Let's look at example number 1. Here's h of x. The first thing I'd like to find are my asymptotes. So I'm going to put my vertical asymptote, VA. Now that comes from the denominator. Now somebody was nice and they already factored this denominator. So it looks like there's going to be 2 different values that could make a 0 in the denominator. So we're going to have 2 vertical asymptotes. In this case, one of them is going to be x equals 3. And the other one is going to be x equals -4. So this is the first time that we've actually had 2 vertical asymptotes. I'll go to when x equals 3 and dash that in. And then I'll go to when x equals -4, 1, 2, 3, -4, and I'll dash that in. So we can already see that this is a little bit more of a complicated rational function. Let's do our horizontal asymptote. This depends on the degrees. We need to find the degree of the numerator and the degree of the denominator. Well, the degree of the numerator is just 0 because I just see a number. This is like 6x to the 0 power. So the degree is 0, and the denominator, it's in factored form, so if I FOILed this, I'd realize that there is going to be an x squared. So the degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, that's case number 1 from our previous notes, it will always be y equals 0 in that case. So that's the x-axis. Y equals 0 is the x-axis. I'm going to dash in my horizontal asymptote there. Next, let's look for our x-intercept. Our x-intercept comes from the numerator. I'm going to set the numerator equal to 0, and then I'll be confused because obviously that doesn't make any sense. And if that doesn't make any sense, that means that there is no way to make the numerator equal to 0, so therefore there is no x-intercept. And that should make sense if we look at our graph, because we have a horizontal asymptote covering up the x-axis, so typically we wouldn't be touching an asymptote, so there shouldn't be an x-intercept. Let's find our y-intercept. When we're looking for our y-intercept, we are plugging 0 in for x. So our numerator, of course, is still 6. Our denominator becomes 0 minus 3 and 0 plus 4. Quick doing this math, we get 6 divided by negative 12, which is negative 1/2. So our y-intercept, I do like to put it as an ordered pair, is going to be 0, negative 1/2. Let's plot that. That would be approximately right there. Before we do domain and range and end behavior, let's now plug this into the calculator and see what our graph looks like. Now, remember, when we're plugging into the calculator, we want to make sure that the entire numerator is in parentheses and the entire denominator. Well, the numerator is just one thing, so again, I don't really need to worry about that. It doesn't hurt to put a set of parentheses there, but this denominator needs to be in parentheses. Even if you see existing parentheses, you need to put parentheses around the entire denominator that you see. So let's go into the calculator, bring this over here. And let's see, I'll put the 6 in parentheses. It doesn't hurt to put the entire numerator and the entire denominator. Now I'm going to start the denominator's parenthesis and then do the parentheses that I see, x minus 3 and x plus 4. And then close the denominator set of parentheses. Again, the calculator needs to see the entire denominator. If you mess that up, don't worry. When you push graph, you're going to see that your graph is not going to actually fit into your little shell, your little skeleton. Okay, so this is a more complicated graph. Hopefully you can translate what that looks like into where it's supposed to be in your graph. So I see that, and I see that there's a curve right here. So I'm just going to sketch this in, getting closer to the asymptotes without touching it. In this middle piece, we have this, I don't know, iceberg looking thing. So I'll do that. Make sure that you go through the y-intercept that we've already plotted. And then in this section, we had this piece. We could get more detailed with, plotting points, but I don't think it's that important right now. I do want you to have your x-intercepts and your y-intercepts correct. Okay, domain. I like to do set notation, and I'm going to do domain. Actually, I'm going to color code it with the vertical asymptote, so I'll do red. The domain, all x such that x is not equal to, in this case, there are two values, 3 and negative 4 are no good. If you want to do set notation, that's what I would prefer. If you do interval notation, you'd be describing 3 intervals this time, from negative infinity to negative 4, and then union that with negative 4 to positive 3, and then union that with the third one, positive 3 to infinity. It seems to be a lot more writing, so I'm going to do set notation. Now, range is a little bit trickier, like I said, with these more complicated graphs. In this case, range is not just everything except for this blue horizontal asymptote, because you can see there's a lot of numbers right in between negative 1/2 and 0 that we actually don't touch. I'm going to have to use set notation. It's a little bit easier in this case, and I'm going to start down here at negative infinity and get as high up as negative 1/2. And that's going to be my first interval, from negative infinity to negative 1/2. Now, I know that I get to include that negative 1/2 because there's a nice solid dot. So this time I get to use a bracket. And then I'm going to union that with the rest of my range. I don't have any more of my graph until I get above the horizontal asymptote. So I'll start here at 0 and get all the way to positive infinity. But this time I don't get to include the 0. Because it was on a horizontal asymptote. So the range is a little bit trickier. Finally, our end behavior, you can see that both ends are still trying to level out right at the value of the horizontal asymptote. The left end, the right end, they're both doing the same. So I'm going to say as x approaches positive or negative infinity, my function is called h of x, is trying to approach 0. Okay, so let's look at example number 2. And let's do the same stuff. I'm going to go in the same order, and I'm going to try to use the same colors. Vertical asymptote first. Well, I only see one thing in the denominator, and that means that x cannot be 0. X equals 0 is my vertical asymptote. It covers up the entire y-axis. My horizontal asymptote, that depends on my degrees. The degree of the numerator is 1. The degree of the denominator is 1. This is a different case from example number 1. This time the degrees are identical. They're the same. And if they're the same, then we take the leading coefficient. And the leading coefficient is 1 divided by 1. So y equals 1. All right, that's a lot of 1s. Y equals 1 is right here. This horizontal asymptote. Okay. Next, let's look for our x-intercept. Our x-intercept comes from the numerator. We set the numerator equal to 0. This time we do have an equation that we can solve, and it's x equals 1. So it looks like we do have an x-intercept. I'll put it as an ordered pair, 1, 0. And let's plot that. 1, 0. That'll help us with our curve. Next, we'll find our y-intercept. Our y-intercept comes from setting x equal to 0. So in this case, we have 0 minus 1 in the numerator and 0 in the denominator, or rather negative 1 divided by 0. Wait a minute. We know that we can't divide by 0, so that means that there is no y-intercept. And that, again, it should make sense because we've covered up the y-axis with this vertical asymptote, so we shouldn't be able to touch the y-axis. So there is no y-intercept. Before we do domain, range, and end behavior, let's plug it into the calculator. And here's my calculator with my previous graph. I'm going to go to y equals and clear that out. Again, please make sure you have parentheses around the entire numerator, around the entire denominator. Doesn't really matter for this denominator because it is just one thing, but that numerator definitely needs to be housed in parentheses. And like I said, it doesn't hurt to put the parentheses everywhere. I'm going to press graph and make sure that it fits into my little skeleton shell here. Sure, looks nice. I know that this curve, this piece of the curve does this. And this piece, again, we have the x-intercept that helps so that we know that we go right through that. Let's talk domain. The domain is everything this time except for that 0. So I'll say the set of all x such that x is not equal to 0. You could do interval notation if you wish. Range is not too bad this time because it is just this value of 1 that is not touched. We go from negative infinity all the way to this 1, though we don't touch it, and then we pick up right past 1 and we go the rest of the way all the way to positive infinity. I'm going to do that in interval notation, all y such that y is not equal to 1. Some people, especially with range, it's sometimes easier to do with interval notation. We'll go from negative infinity to 1 and then union that with 1 to infinity. Sometimes with the range it makes more sense to do interval notation. We don't always luck out and get that it's just a single value that we are not equal to. Finally, our end behavior. This should be becoming easier for you. Both ends typically do the same thing with rational functions, and they both approach the value of the horizontal asymptote, which is the value of 1. Check the name. It is k of x this time, and it is approaching the value of 1. Let's turn over and look at example 3. This is our final example for this tutorial, and let's go and find our vertical asymptotes again. We start off with that. Uh-oh. Somebody did not factor this denominator this time. So it looks like we're going to have to factor that. And that's not too bad. That's just a difference of two perfect squares. And I'm going to factor that into x plus 4 times x minus 4. Okay. Once it's in factored form, it's a whole lot easier to see that we do have two vertical asymptotes. One's going to happen at x equals negative 4, and one's going to happen at x equals positive 4. And just so I can be fancy, I'm going to use a plus or minus symbol. So I have two vertical asymptotes again. One is going to be at positive 4, dash that in, and the other one's going to be at -4. We'll dash that in. Okay. Horizontal asymptote, that comes from our degrees again. And let's see what we've got here. The degree of the numerator is a 2. The degree of the denominator is also a 2. So it's that second case again where we take the leading coefficient, and in this case that's -3/1. So y equals -3. I'll dash that in. This is 1, 2, -3. And there we go, starting to create our shell. Let's do X-intercept. X-intercept comes from the numerator. That was a little too much there. X-intercept comes from the numerator. -3x² is going to be set equal to 0. And we solve this. Well, that's not too bad. If I divide by -3, I will have x² equals 0. And if x² equals 0, that means that x has to be 0. So it looks like 0, 0 is our x-intercept. So we're crossing at the origin. It's kind of a giveaway as to what our y-intercept is, but let's prove it mathematically that the y-intercept will also be 0, 0. I'm going to use this form, the version that they gave me, -3 times 0 squared and 0 squared minus 16. To find the y-intercept, I'm just plugging 0 in for x. So that means in the numerator I get 0, and in the denominator I get -16, and that of course is 0. So the y-intercept has been proven also to be 0, 0. Domain and range and end behavior I like to do once I've graphed it. So now let's plug into the calculator. Let's put the numerator in parentheses. Let's put the denominator in parentheses. If you use the original problem, that's great. If you use the factored version, that's fine as long as you put parentheses around those parentheses. So where'd my calculator go? There we go. Y equals, let's clear out that, and I've got -3x². Close the parentheses, divided by, I'm doing the first one, which is x² minus 16. Put that in parentheses. And I'll press graph and see if it fits into my shell, which it does. A nice looking symmetrical graph with this piece down here and symmetric over here. And then in the middle, we've got this, it's not really a parabola, but for lack of a better name, I'm going to call it a parabola type thing. Right there. Again, we're crossing right there at the origin. Okay. Domain, I know we could have done domain before looking at the graph because the domain is basically the values of the vertical asymptotes. I understand that, and I'm going to do that right now. I know that the range is trickier unless we're looking at the graph. X cannot be equal to +or-4 for the domain. My range, I need to look at the graph. Again, I'm going to use interval notation because there's a bunch of numbers that are not used in my range. All of this stuff in between this -3 and this 0. So range, I always like to start as far down as I can, and I see an arrow pointing all the way down, so that must mean that we're starting at -infinity. So I'll start there, and let's see how high we go up. We go from -infinity all the way to, well, it looks like we level out right here at this horizontal asymptote, this -3. In fact, we don't even touch it. So we get as far as the -3, but we don't touch it. So not touching uses a parenthesis, and then we'll union that. Let's see where we pick up our range again. We skip, 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 skip a bunch of points until we get to this 0. And we get to include the 0 because that is an ordered pair. It's a solid dot right there. So we're using the 0, and then let's follow up, and we go up all the way to +infinity. So we do not include the -3. That's the parenthesis, but we do include the 0, that's a bracket. Last thing to do here is our end behavior. As x approaches, it doesn't matter which end we're talking about. The far right end approaches the horizontal asymptote. The far left end approaches the horizontal asymptote. It's actually not even going to touch it, but m of x is trying to be -3. It's approaching -3. Thanks for watching this tutorial. We have one more example in our second tutorial, and I'll see you in class. Oh, thanks. See ya.